Okay, good morning, everybody. We're getting ready for our exam on Friday. There will be 25 multiple choice questions on this. Most of the time when I give exams live, I usually have some part which you actually write and do mechanisms and stuff. But because we can't do that because of the way we are so distanced, that's why I have those activities. And so those activities go to let you practice drawing and doing. In fact, I've talked to a couple students who actually they can buy graph paper that's done in hexagons, so it makes it really easy to draw out structures for the first few times you have it. I don't know if you've seen that. It's called something like Hexcel, and it's available on Amazon. So if you wanted to do that, buy a few sheets of that and practice your drawing, that would be great. What I plan to do is I plan to go over my slides, my review slides that I have posted to Canvas. Okay. And I would like to, if I have time, to go over the activity. So I can go over the activity and explain why and how and what. And so that's actually going to be the perfect end capper because my review slides go all the way through Sn1, Sn2, E1, E2, trying to figure out how each of them are. And the exercise was basically helping you look through, is it a good nucleophile? Is it a good base? Is it a good leaving group? Does it form a carbocation? What kind of solvents do it? You know, and so that was the intent of the activity. And so that way I want to end with that activity on there and so that we can go through it and talk about it together, okay? So let me go ahead and share my screen with the slides that I posted to Canvas. This is the review. And this is just like before, it's basically the hot topics. These are the topics that you need to make sure you are very familiar with. And then if you're not quite sure what to do, go ahead and look at that topic and look around the little ancillary information around that topic. It would be very useful for you. So I'm going to go ahead and share my screen. Okay, one thing I would like to do is I'd like to have somebody unmute and talk to me to see if while I'm recording, I can actually hear people, because I think I've solved that problem, but I'm not sure.
Good morning, Dr. Irving.
Yes. Okay, yeah, great. All right. So
hello, hello.
I can hear you. I can hear you. Can you hear me still?
Well, good morning.
Okay. Good.
Yeah.
All right.
Hear you.
All right, let's go ahead and start our review on this. So this review starts at chapter 5, which is stereochemistry, and it goes through chapter 7. And then the chapter 7 capper is that comparison of E1, E2, Sn1, Sn2. And we'll end with that. That does not mean we are not going to do anything from the first 4 chapters. Those are going to be kind of interdispersed in there, like nomenclature and stuff like that. So don't forget any of that. In fact, you need a little bit of that to build on what we're doing here. So, but this is what the exam is going to be focused on. We'll have 25 multiple questions, and it'll be on Friday at our normal class time. Do not come to Zoom, go directly to Top Hat and get your Proctorio set up. Okay. So chapter 5 started with stereochemistry, and we had 2 types of stereochemistry we talked about. We talked about chirality, which is an sp3 hybridized stereochemistry, but then we also talked about E and Z, which is an sp2 hybridized stereochemistry. So we got to make sure we think about both of those. And then within this, we have different kinds of things. Isomers, like structural or constitutional isomers, are hooked up differently. Stereoisomers are hooked up exactly the same, but are different in space, okay? That's how we get those 4 different objects in space. And then once we have the chirality, we have enantiomers, which are mirror images, but non-superimposable. And if we have more than 1 stereocenter, then we can have sets of diastereomers, okay? So you always have a pair of enantiomers and you have sets of diastereomers. And because of mirror planes, one of the stereoisomers can actually cancel the other one out, and we only have a non-chiral part. That's why I say a set of diastereomers, because there can be like 3 compounds in your set of diastereomers or more. All right, so the first thing we have is our more straightforward stereochemistry, which is our E and Z. We just need to remember that E is opposite and Z is same side. So when we look at this, remember how to do the stereochemistry. We start at 1/2 of the compound right here and find priority, whichever 1 or 2 is on this side. And then we looked for the priority on the other half, 1 and 2. Okay, in this case right here, 2 is highest priority on each of these compounds, and they are on the same side, which makes them cis if we only have 2 things attached, or Z if we have more than 2 things attached. Okay, so the Enz system has everything to do with the 3 rules. The 3 rules are atomic number first. If atomic number solves your problem or identifies priority, you're done. If atomic number does not solve your problem, then you have to go to the next atom over. For example, if you had 2 things that had carbons, what's attached to it next? And therefore, the next highest priority thing on there is what you use. So if you had an oxygen on one and a chlorine on the other, the chlorine's higher in atomic number, therefore it takes priority. Now, if you can't solve the problem there, or you have a double or triple bond, or in this case, according to the slide, it's a double bond, but that's another story. I'll fix that in my thing. So you have to count each of the bonds as connected to an atom. So if you have a double bond to a carbon, you have to count carbon once and then carbon the second time for the second bond. And if you have a triple bond, you have to count carbon again. And then once you find a difference, then you have priority. Okay, questions on Enz? Okay, so then we got to the slightly more complex, because you had to do it in 3D space, the chirality. Now, the first thing to always look for chirality is 4 different things attached to your chiral carbon. And then you have to determine what the priorities are and get it to be R for clockwise and S for counterclockwise, okay? Now, whenever you draw your structure, you should be able to draw a mirror plane and draw the opposite structure that it was equal, and I'm sorry, the mirror image. And when you draw that mirror image, if they're non-superimposable, they are chiral. If they are superimposable, they are achiral or not chiral. Okay, and remember that chiral compounds have an optical activity associated with them. If R is rotating light negative 30 degrees, S will rotate light positive 30 degrees. And no, you cannot predict whether it's going to be positive or negative based on whether it's R or S. Okay, go ahead and make sure that when you do your R and S, you use the exact same priority system you used for the E and Z. Okay, atomic number, and then the next atom over, and then double and triple bond rule. Those same 3 rules assign priority in our R and S system. Okay, now what if you have more than 1 stereocenter? If you have more than 1 stereocenter, then you have the possibility of diastereomers. How many diastereomers you have? Well, it's going to be 2 times the number of stereocenters you have. I'm sorry, 2 to the power of the number of stereocenters you have. So if you have 3 stereocenters, that's 2 times 2 times 2, which means you have 8 possible isomers available to you. So, but then you have to keep them straight. Now, within that set of diastereomers that you have, you're going to have a pair of enantiomers and hopefully another pair of enantiomers. But if there is a superimposable system in one of the sets, it turns into meso and it goes away and it becomes achiral. Okay, it still exists as a single molecule, but it is achiral. So that's why we have to pay attention to that. Now, also remember within these chiral compounds, especially when you have rings or multiple substituents, look for mirror planes. That mirror plane will eliminate some of the stereochemistry, like in a meso compound. Okay, so this slide I like because it's basically showing you what they're drawn like and how to draw from just your 2 chiral carbons the way it would be drawn with wedges, and convert it into the Fischer projection. The Fischer projection makes it easier to do your diastereomer drawing because you can draw that mirror plane and make the enantiomer. And then by switching one of the bonds, you get to the diastereomers. So in this right here, knowing the difference between your pair of enantiomers and then your set of diastereomers is important, and being able to convert from a drawn structure to this to help you identify each of those isomers. Okay. And don't forget those tricky little mirror planes. Any plane of symmetry will remove chirality from a system. Okay. And when it removes chirality from a system, we call those meso compounds. Okay. So the net review, this is basically the review of the entire chapter: isomers, constitutional structural isomers, stereoisomers, the two types of stereoisomers we have, the idea that we have enantiomers and sets of diastereomers. Okay, any questions on stereochemistry and how we assign that? We had a good activity on that, and so I think that really, hopefully, really drove the concept home for you. Okay, so the next chapter was Module 6, okay? And the first thing we learned in Module 6 is that we are going to, for the rest of organic chemistry, be looking at different kinds of organic chemistry. And most of these reactions, not all, but most of these reactions can be defined as a substitution reaction, which is replacing something, an elimination reaction, which is losing something, an addition reaction, which is adding something across a double bond or triple bond, and then a rearrangement, for example, a carbocation rearrangement. Okay, so we're going to see these kinds of things in all of our E1, E2, Sn1, Sn2 reactions. And when we move on to other functional groups, we're going to see that we can do different things to like an addition across a carbonyl. And that's going to give us a different product. And so we'll see these same types of reactions again and again and again. Okay, so and then we learned a lot about energy diagrams or coordinate diagrams. Now the coordinate diagrams tell you a lot of things. And so being able to identify the different parts of the coordinate diagram are important. For example, we have our starting materials and our starting energy. And then we have our products and our ending energy. And knowing that whether your enthalpy is positive or negative, whether you gave off heat, like in this case, when your enthalpy is less than your starting materials, that means you gave off heat in this reaction here, okay? So knowing that is important. Knowing that there's an activation energy, an energy required to get to your, in the case of a one-step reaction, your transition state, okay? Your transition state, that barrier is, of getting through all of the electron density to get to where you're starting to form a bond. That's the energy it takes to get to that place where you've pushed past all those electrons trying to force you away, and you're starting to form that new bond. So that's that transition state. In a one-step reaction, we call those concerted because it happens all at once, okay? So, and this is an example of something like an Sn2 reaction, the bimolecular reaction, where you do a substitution and it happens all in one step. Then, of course, we got to look at our two-step reactions. And in a two-step reactions, we have that extra hump, but we also have a new thing we didn't have in the one-step reaction. We have the intermediate, okay? So in this case here, we always form an intermediate in there. And for this module in particular, and module 7, we learned that intermediate is a carbocation. So in our E1 reaction and our Sn1 reactions, we form a carbocation as our intermediate. Now, we still have our activation energy to form that, which is breaking that bond. We have to add enough energy to break a polarized bond. And then we want to see that this intermediate is as stable as possible. Okay, so we're going to talk about carbocation instability a little bit. And then the next thing is trying to get your nucleophile to react with that. So it still has to push against electron density. So there's still another activation energy barrier. And then of course your products. And if your products are up here, then it absorbed heat to make the product and you have an endothermic reaction. And if you're down here, you have an exothermic reaction. So make sure you know the difference. And if you have to focus on one or the other, I would focus on enthalpy instead of Gibbs free energy, because they are directly proportional with our temperature and our change in entropy, but they tend to be, in most of the reactions we see, they tend to be fairly fairly analogous to each other. Okay, so then we also have to know the difference between kinetic and thermodynamic. Okay, kinetic is related to the rate of the reaction, and the rate of the reaction is typically directly associated with the activation energy, getting to that transition state, okay? If it's hard to get to that transition state, or you have a huge energy, you have huge activation energy, that means the reaction is going to go slow. Okay, it doesn't mean you have a better or worse product. It means that it's just going to go slow. If you have a small activation energy, it's going to go fast. Okay. Now, thermodynamics, the thermodynamic product is the one that has the less stored, less potential energy at the end. You want the one with the least amount of potential energy at the end. That means it has given off as much of its heat as possible, and that's the thermodynamic product. Okay. Can you be the kinetic and thermodynamic product at the same time? Yes. They are not mutually exclusive. So they are separate and they are not equal. Okay. So that led us into the next reaction set we took. We talked about nucleophiles and electrophiles. Okay. So electrophiles are always electron deficient atoms. That doesn't mean they have a positive charge. It just means maybe they don't have a full octet. Okay, so for example, aluminum chloride has an electropositive, a partially positive aluminum atom in there, and that makes it the electrophile. All Lewis acids are electrophiles. Okay, so remember your Lewis acid, Lewis base, definition, because it fits right into this nucleophiles and electrophiles. Our nucleophiles are those that are electron rich. Think about things with electron pairs or a negative charge. Okay. And so that pulls up something like this. So we can look at these different nucleophilic sites. Okay. When you have a polar bond with the carbon being the more electronegative site, you can have the carbon being a nucleophilic site. Okay. The lone pairs on oxygen are a nucleophilic site because those are electrons ready to donate. And the pi bond is usually the nucleophilic site because those electrons are available to bond to something else to form a new sigma bond. Okay. In the opposite of that, carbon can also be an electrophilic site. If there's a more electronegative atom making a polar bond, that carbon is partially positive, and therefore it is a site for the electrophile. Okay. If we have a carbocation, an empty p orbital, that is an electrophilic site. And if we have an electron deficient atom like boron in this case, or aluminum, that is also an electrophilic site. Okay.
I have a before you move on, so I remember, we still are you said to focus on enthalpy and entropy because they're analogous, but it's still good to know about I mean, you said it would focus on
enthalpy as opposed to Gibbs free energy, because
okay.
they are proportional in most of the reactions we do.
Okay.
Okay. So if you're giving off heat in a system, you actually are giving up free energy as well.
Yeah.
So that's the point. It's just that I think heat is a little more tangible.
Okay.
We can think of, because how do you measure the free energy? Well, you actually measure the enthalpy and then calculate the free energy. So we usually just measure the temperature anyway. So that's why I say that. Okay.
Yeah.
All right. So now we have nucleophiles and electrophiles and how they directly relate to Lewis acids and bases. Okay. So now let's talk about our Sn1, Sn2. They have two completely different mechanisms, right? Sn2 is a bimolecular reaction. It has one transition state, and both of the things have to be there at the same time, okay? So they tend to be exothermic or exergonic, meaning they give off free energy or they give off heat. And they can form the thermodynamic or the kinetic product based on the height of the activation energy. Okay. So in contrast, your Sn1 must form that carbocation intermediate, making it a multi-step reaction. It has at least two humps. If you are attacking your carbocation with a neutral species, you have to lose a proton. So there's a third hump. But if you're attacking it with a negative, like a negatively charged species, like a chlorine or something, then you only have the two humps. So there's at least two humps and at least one intermediate in your Sn1 reactions, okay? And again, most of these reactions do give off heat. Okay. So let's look at the rate law associated with these Sn1 reactions. Okay. Because it's unimolecular, because it has to form a carbocation first, it only depends on the concentration of your substrate. Because nothing happens until that substrate breaks a bond and forms that carbocation. Okay. So it only depends on the concentration of your substrate. Okay. So if you double the concentration of your substrate, you double the rate of the reaction. If you double the rate of the nucleophile, it doesn't matter because you have to form that carbocation first.
Substrate means electrophile, right?
Substrate means whatever it has your leading group on it. So it's
Okay.
usually the organic molecule that ends up being a part of your product. Okay. It's the thing
Okay.
substituting something off of.
Oh, okay.
Okay. So whichever one of those things is consistent within, you know, your vernacular, use that. Okay. And being Sn1 reactions, and we have to form that carbocation, we always have at least 2 humps in our coordinate diagram. First thing we do is we break a polar bond, we make a carbocation, and then we have the coming in of the nucleophile to create our new sigma bond. Okay. So know each of the parts of these reaction coordinate diagrams. Okay. We also learned that polar protic solvents enhance the formation of the carbocation. It enhances the stability of the carbocation, and therefore it enhances the rate of the reaction. So we're looking for polar protic solvents to help the Sn1 reaction. Is there still loud static now? I thought I heard it go away. Does anybody else?
I hear fine right now.
Okay.
It might just be specific to that person, to your internet, whoever's saying that.
Okay. Some yes, some no. Okay, so it might just be quiet sometimes. Okay. All right. Well, hopefully I'll
You
just,
might want to just leave the call and come back. Like, honestly, that might fix it.
yeah, that does fix it a lot of times. So I'm gonna, this is being recorded so you can always look at that. So because we're forming our carbocation here, we need to know our order of carbocation stability. And you kind of need to know why it's stable, but why it's more stable. So go ahead and look that up. But our tertiary carbocations are more stable than our secondaries, and we rarely form our primaries or our methyl cations in organic chemistry. It takes very special conditions to be able to do that. So think about your tertiaries and your secondaries being more common. Okay. That being said, if you have a secondary and it wants to become a tertiary because it's more stable, and we have 2 ways to do that. We have a 1,2 hydride shift. Remember, we call it a hydride because both of the electrons from the hydrogen are moved over to where the secondary carbocation is to form our new tertiary carbocation. Now, if we don't have a methyl group to move, if we don't have a hydride to move, we can move a methyl group. Rarely do you move anything bigger than that unless it's a ring. And the reason you can open a ring like that is because of ring strength. So the only time you do more than a methyl group is when you have a ring. And I think I gave 2 examples of that during class, so double check that. Okay. So in contrast, our Sn2 reactions are 1-step reactions, and it depends on the concentration of both the substrate and the nucleophile. So if you double one, it goes double. If you double the other, it goes double. If you double both, it quadruples. Okay. So because our transition state has to have the nucleophile and the substrate in the same place at the same time, that's why it's number 1 bimolecular, and that's why it depends on both concentrations. Okay. So our mechanism is a little bit easier. Our coordinate diagram only has 1 hump. And our activation energy has everything to do with getting your nucleophile past all of the electron-electron repulsion to get to start forming that new bond. Once you start forming that new bond, you start to cascade down into products. Okay, so we learned that unlike the Sn1 reaction, where we're looking for a polar protic solvent and the ability to form a stable carbocation, we have a couple different things that affect our SN2 reactions. We actually have 4 things. One is the nature of the leaving group, how polar that bond is, and how good a negative charge, let's see, I don't want to say soft. I want to say how stable that negative charge is when it leaves. So if it's big and can stabilize that charge over a large amount of area, it's going to leave better. And so it's going to be a better leaving group. The reactivity of the nucleophile, okay? So we have good nucleophiles, really good nucleophiles that have negative charges and nitrogens and sulfurs. And then we have our intermediate ones, which are oxygen, anions, and some of our neutral nitrogens. And then we have our poor nucleophiles, things like acetate ion and water and alcohols that are protonated and only have lone pairs. So the reactivity of the nucleophile is going to give us an idea as to rate and or condition. Okay, then solvent also affects it as well. It's not a requirement to have a polar protic solvent as it is in an SN1 reaction. However, polar and charged solvents can have a large effect. And this is especially important when you have halides. The halides, if you have a polar protic solvent, it changes the reactivity of the halides, okay? In a non-polar, in a polar aprotic solvent, your iodine is the better nucleophile. In the protic solvent, it's the other way around. So watch out for that.
In what? You said polar twice.
Polar aprotic and polar protic.
Oh, yeah.
Most of these reactions have to take place in a polar solvent to support the charge.
Yeah, sorry.
Yeah, and there's a table on that where we actually did the same reaction in a bunch of solvents, and once you got to hexane, it almost didn't happen at all.
Yeah, so it's in aprotic, it's better for iodide. Is that?
Go look.
No, it's better for fluoride in aprotic.
Go look at the series because it has everything to do with acid strength.
Okay, yeah.
So you can look at the acid strength and polar and non-aprotic and protic solvents and see the trend reverse. Okay. The last thing we have is the structure of the electrophile. And because it's an Sn2 reaction and you have to be both at the same place, that means the less sterically hindered the electrophile is, the faster the reaction will go. So think smaller primary halides and unhindered halides. Secondary halides, they can go Sn1 or Sn2 based on what kind of solvent you have in there. Once you get to a tertiary, it almost never goes Sn2, okay? Because that's the structure of the electrophile, okay? So think about that as really being sterics.
Dr. Irvin?
Yes.
So is there no like general rule of like what makes a good nucleophile? Should we just memorize like which ones are generally good nucleophiles?
We're actually going to talk about that, but there are good things. Yeah, there's 3 factors on it. One is most good nucleophiles have charge, okay, and it's a polarizable charge, okay, and then next below that is acid, the conjugate acid strength, okay, and I have a table for that. We're going to go into that in a minute, but there is a trend and there is things to look for. Polarizable negative charges are better nucleophiles. Things that are strong conjugate acids are better nucleophiles. Things that are that have charge spread out over more than one atom actually become poorer nucleophiles because your negative charge isn't on one atom all the time. Okay, so we have that. We're going to look into that in a minute. Okay, and I'm going to compare and contrast that at the end. Okay. Now that we have our Sn1 and Sn2, let's look at our E1 reaction. Our E1 reaction, just like the Sn1 reaction, forms a carbocation. And therefore, Sn1 and E1 reactions typically compete, okay? Unless you use a lot of heat and a really, really strong base, they will always be a little bit of competition between Sn1 and E1 because of the formation of that carbocation. But that E1 has that 2-step mechanism where we form our carbocation, and then the next thing that has to do is you have to remove a proton from a beta carbon, okay? Remember, You've already removed your leaving group from that alpha carbon, so you have to remove a hydrogen 1 carbon over to give us our double bond. Okay, so that's the elimination reaction. So we have to look at the products based on where that beta proton has been removed. Now notice in this case right here, we're using ethanol as our solvent, and it turns out it's a polar protic solvent which promotes the formation of a carbocation, but we have a lot of Sn1 as the product and some E1 as the product. So we have to look at the nature of that, the solvent, to help us identify our products. And we have a compare and contrast at the end. Okay. Now, which beta hydrogen remove is if we don't have a big bulky base, you follow Zaitsev's rule. Zaitsev's rule says you will form the more substituted double bond. Okay. Zaitsev's rule says you will form the more substituted double bond if you have a small non-hindered base. Okay, so you got to remember that. E2 reactions are different because you have the leaving group leaving at the same time the base is pulling on your beta hydrogen. So that's why it's bimolecular. Your base has to be adjacent to a beta hydrogen pulling on it. Those electrons will kick in, forming your double bond. Then the sigma electrons on your leaving group kick out, forming your stable ion. Okay. So that's the big difference between E1 and E2. And E2 reactions rarely compete with Sn2 reactions when you have strong bases, but they can if you have little tiny bases. You can get some substitution products. Okay. So in this case here, we have a very small base. We have the methoxide right here, and we're in a protonated solvent here. And so we actually end up doing a bunch of the substitution because that's a very tiny base and it's a primary halide. Okay. So you have the opportunity to do your Sn1 because you have a good nucleophile and a primary substrate. So that favors Sn2 reactions. But we still get some elimination. There's still some competition here because it's a strong base. Now, by changing the nature of the substrate, changing it to secondary, we've now decreased the rate of reaction of the substitution reaction. Just going from a primary to a secondary, that decreases the rate, right? And now that promotes the rate of the elimination because we still have a strong base, but we've decreased the rate of our substitution. Therefore, our elimination product becomes our major product. Okay, so you can think of it, the reaction still happens, but the rate is lower. And by the time we get to our tertiary substrate in a protic solvent, we're forming probably, we are really not going to do a substitution reaction at all. So we actually get 0 substitution reaction, and we get 100% of the E2. Again, this is a strong base, so we don't have to wait around for a carbocation to do the elimination, and therefore it's an E2 reaction.
I have a question. It's kind of a basic question, but I still would want to know.
Well, it's better than an acidic.
Is you said that CH3 ONA there, that was a good base.
Yes.
But it's like a neutral compound. Like, how do you?
No, it's not. It's CH3O minus sodium plus.
Okay.
There's actually, this is the alkoxide. This is the deprotonated alcohols. Remember, alcohols are not very acidic, so their conjugate bases are very basic.
Okay.
So all deprotonated alcohols are strong bases.
Okay.
Okay.
Alrighty.
All right. So the mechanism of our E2 is our base has to be tugging on a beta. Okay. And it has to be tugging on a beta hydrogen. Therefore, concentration is base. I'm sorry, the concentration of the base and the substrate are important for this. Okay. Now, the only thing that gets in the way is sterics. We have to, if you have a lot of groups around something and there is a competition between that, we have a steric issue. Okay. If we have small bases, we always tend to form our Zaitsev's product because it can get in and remove the hydrogen that will give us the more substituted product. However, if we don't have that, we end up getting a different product. And we'll talk about the Hoffman product in a minute. Now, because it's bimolecular, we have a specific orientation where the hydrogen has to be preferably anti to the leaving group. So you have to think about this as far as sterics go, and maybe in a ring, if you can't get the hydrogen anti to our leaving group, as shown in this configuration here, our Newman right here, that allows the electrons to kick in, form our double bond, and our electrons to kick out with our bromine and make that reaction happen quickly. It can happen if they're on the same side here, because again, these electrons are kicking in while these electrons are kicking out, but it's rarely in that configuration because of the, it's less stable in that form. And if you cannot get your hydrogen into an anti-position with your bromine, the reaction won't happen at all. Okay, if your leaving group and your hydrogen are in a gauche position, they will not react. Okay, so that is kind of important for your E2 reactions because the base has to be there at the exact same time as your leaving group. Therefore, this kind of stereochemistry is related to E2 reactions. Okay. Now, what happens if your base starts to get really big and your base cannot come in and get your secondary beta hydrogens? Okay. So ethoxide and methoxide, CH3O-, we consider these small, non-bulky bases because they just have a straight chain behind them. That negative charge is right up front, and it can easily get in to find our secondary hydrogens. And when we do that, we get the more stable product, the Zaitsev product, as our major product. Okay. But once we get to these bigger, bulkier bases, T-butoxide is classical, and then something else like that. We also have another one called LDA. These can't now go here at all. So they end up going to the less bulky methyl groups on the end, giving us our less stable product, but the rate of the reaction for these hitting here is much higher. Therefore, it becomes our major product. It has everything to do with the size of the space. So if you see T-butoxide or LDA or something like that, we're looking at forming the Hoffman elimination product, which is the less stable. It takes it off the least sterically demanding beta hydrogen. Okay, so to compare the two rules together, right here, small base equals Zaitsev's rule, big bulky base equals Hoffman's rule, okay? Because the activation energy for getting it to the less bulky base is smaller on the methyl group here, even though it gives the thermodynamically unfavored product, that activation energy controls the product. Now notice in the Zaitsev's rule, the activation energy is lower for the hydrogen on the more substituted carbon. So we have both the thermodynamic product and the kinetic product. So that's why thermodynamic and kinetic products are different and not equal, and you can have one or the other or both in the same reaction. Okay. All right. Okay, I think we're doing well. All right, so this leads us to how do we do all of these? Okay, there's like, oh my gosh, they're so complicated. No, they're not that complicated. Sn1, E1, you got to form a carbocation. You need a good solvent and a good leaving group to form that carbocation. Think good leaving groups like iodine and bromine and a polar protic solvent, water, methanol. Those are going to start favoring your Sn1, E1 reactions. Okay. Now,
When you mean good leaving group, you mean they have to be weak, right?
They need to be
Weaker than the nucleophile file.
Correct.
Okay.
You want the so you need something that's a decent nucleophile but not a very good base. So think iodine or neutral molecules. If you like when we did our elimination of an alcohol, what we did was we protonated the alcohol and it left as a neutral species. Then it's no longer reactive, right? It can only act as a base at that point. It can't act very nucleophilic.
Yeah.
Okay. So Sn1 and E1 look for polar protic solvents and good leaving groups. Sn2 and E2, the difference is, do I have a good nucleophile? Okay, that's the first thing. If I have a good nucleophile, now is it a good base or not? Okay. If it's a poor base but good nucleophile, think substitution. If it's a good base, and if it's also a good base or a strong base, start thinking elimination. Okay. So that's the general place to get it. Okay. So nucleophilicity and basicity are not the same thing. Nucleophilicity has everything to do with the ability for it to attack at that carbon. Okay. So think, nice, stable ions, anions in particular, or things with double bonds. I'm sorry, lone pairs. Okay. Basicity is directly related to its conjugate acid. Okay. Okay. So if the conjugate acid was a very strong acid, that makes it a very weak base. If its conjugate acid is a very weak acid, it's a very strong base. So see how the order changes here. So this is a very good nucleophile, but a very bad base. Okay. And if we looked at the pKa of the conjugate acid here, it's like -7. That's why it's a bad base. Okay. But it's a big polarizable anion. That's why it's a good nucleophile. Okay. So keep that, look at that stuff and try to get that kind of ordered in your head. Okay. And then again, weak nucleophiles can be things that have very small charges, non-polarizable, or shared charges over multiple atoms. Okay. So then we have to think about the size of the nucleophile. If the nucleophile is too big or the base is too big, we cannot use it in a substitution reaction. If it's just too sterically demanding for it to be done, especially on substrates that are secondary or tertiary. It's just too big. You can't get those two molecules close enough to start to form that bond. And therefore, they tend to act as bases and form E2 products. Okay. So when we think of weak polarizable bases, are good nucleophiles. Big fluffy iodine, big fluffy bromine, the sulfur anions, the neutral sulfurs can also be, because they're very large, okay? They mainly produce Sn2 products. Strong bases will promote an Sn2 or an E2 product, okay? Think strong base means, and it's small, means it can get in and start pulling hydrogens off, or it can act as a nucleophile and displace things. Once our base gets too big to actually act for a substitution product, it's going to act as a base only and give you predominantly E2 products. Okay, and then if you have a weak, slightly polarizable base, i.e. something that does not have charge, then you're looking at an alcohol or water. That's going to promote the formation of the carbocation, and it's going to promote our Sn1 and our carbocations, which is Sn1 and E1 reactions. Okay, and this table here that you got on the activity is kind of a summary of that. Kind of, be able to lump these into groups, good nucleophiles, small bases, poor nucleophiles, big bases, weak bases but good nucleophiles, weak bases and fair nucleophiles, and then poor bases and poor nucleophiles, okay? Because those will help tell you which ones you're going to look for, okay? So, and then of course that leads to this right here. This right here gives you nucleophilic strength and base strength here. This side here is talking about your substrate. Methyl groups almost always only do Sn2 reactions because they're small. They can't stabilize a carbocation, and there's no steric demand. Okay, so I'm going to admit, all right. When we get to primaries, you're looking at if it's a good nucleophile, then you're looking at your SN2 as your major product. If it's a strong base, now your elimination product becomes there. If it's a weak base but a good nucleophile, you go back to substitution reactions. So good nucleophiles are going to, good nucleophiles that are small are going to give you substitution products. Good bases that are big are going to give you mainly E2 elimination products. Now, your secondary is the one that can actually undergo all four mechanisms, but it's dependent on what you're reacting it with. And tertiaries almost always go E2 eliminations or some competition between Sn1 and E1. It forms the carbocation. Okay, so kind of come on. So that kind of summarizes that. And then this is for you to read later, this is instructions that you kind of used for the activity, but this is actually set out to what you look for in kind of, not necessarily this order, but it kind of helps you identify these things. And then the secondary things, once you've identified those 6 things, what things can happen, okay? And that gave you, then I gave you this example in the review. Okay. So any questions on that? What I would like to do is after you ask questions, I'm going to switch over to answer some of the activity questions, like 3 or 4 of them in the time we have remaining. So I want to actually step you through stepwise, at least a couple of the different mechanisms and why we chose what we chose as the major or minor product. Okay. Well, you figure out some questions. I'm going to go ahead and switch my screen to the, there it is. Okay, so this is basically this is the review. This is the key that I've posted to Canvas, but I wanted to go over a couple different examples to show you why the answers are what they are. So you were asked in the practice to say, look at this substrate and figure out what the reaction is going to do and what the minor products are. Okay, so, and I showed you that when we looked at it, we identified what was the nucleophile, what was the electrophile, is it a good base, is it a strong base, is it a bulky base, and where the attack would happen. And when we did that, what we found out was because there are no beta hydrogens, it can't undergo any kind of elimination reaction, and therefore our only product is going to be our substitution product. Okay, so let's do that same analysis on the next 3 substrates. Okay, so the first thing we look for here is the idea that number 1, we're in a polar product solvent. Okay, but we have a primary halide, which means we are not going to form a carbocation, which means we're not going to do Sn1 or E1 because we have a primary substrate, so we can't do either one of those. So now we know we need to draw an Sn2 product and an E2 product, okay? So we look at our base here and we know that if this is our alpha carbon, that makes these are beta hydrogens, which is where our base would come in for an elimination product. So that would give us our elimination product as H, CH3, H. So that's our E2 product. And if we use this as a nucleophile, it would come in and displace at this thing, give out that, giving us our Sn2 product, okay? So we have the competition between the Sn1 and Sn2. I mean, sorry, the Sn2 and the E2, which is the major product, okay? Now, because we have a small, good nucleophile, and we have a primary halide, that's going to suggest our substitution product is going to be our major product, and our elimination product is going to be our minor product. Okay, and there we go. We see that that is because primary with a good nucleophile is going to have a fast Sn2 reaction, but we have a primary with beta hydrogens. And so that's still going to give us it's still a strong base, but it's a slightly slower reaction. And therefore our major product is going to be the substitution product. Okay. Now on this one, it also shows that you cannot take that gamma hydrogen. There's no possibility to leave that bromine on there and take away something else. That reaction just doesn't happen. So, all right, so let's change our substrate from a primary to a secondary right here, which would give us practice number 4. Okay, when we change our primary to a secondary, now we have the possibility of E1, Sn1, and we have the possibility of Sn2, E2, okay? Because we can form that carbocation and we are in a protic solvent, so we have a possibility, okay? So we look at our thing here now. We have a good nucleophile and it's a good base and it's not that bulky, okay? And we have a total of 3 beta hydrogens here and 3 beta hydrogens here to give us our product. Okay. So our Sn1 and E1, or our E1 and E2 product is going to give us the same thing. CH3, HHH. And our Sn1 and our our Sn2 product is going to give the same thing, which is going to be CH3, CH3. Okay, so these are our 2 products here. Now, why are we going to eliminate E1 and Sn1 as possible mechanisms? Okay, we only have E1 and Sn1 as possible mechanisms in the absence of a good nucleophile. Okay, we have a polar protic solvent, which would help that happen, but we have a good nucleophile, which means neither one of these is going to happen, okay, because we have that good nucleophile. So now we have 2 choices. We have our substitution product, our Sn2 here, and our E2 product here, okay? Because we have a secondary substrate, the reaction on secondary substrates is slower than that of primary substrates. So that going to make this the major product and this the minor product. Okay, and if we look at the answer, yes, good. Okay, so work through the process of good nucleophile, bad nucleophile, protic solvent, non-protic solvent, bulky base, non-bulky base, knowing that you can have each of those reactions happen and then start eliminating which don't happen. I have a strong nucleophile, therefore I'm not going to form a carbocation. I can eliminate those 2 mechanisms. Okay, of those 2 products, which is going to go faster? Primary substrates do substitution reactions faster than secondary substrates, and tertiary substrates hardly do that substitution at all. Okay, and you can go through the last one here. We have a poor nucleophile in a polar protic solvent. So we're actually going to end up getting our substitution as our major because we have a poor, this is a poor base. So it's a poor nucleophile and a poor base. So our substitution product is going to be the major product. Okay, okay, so sorry, I ran over 3 minutes. If you have any questions, go ahead and ask them now. And if not, go ahead and run off to your next class.
That whole review is posted?
Yes, this both the key and the review are on Canvas.
Okay.
How soon will you be posting the recording for today?
As soon as I get off, it takes about 20 minutes.
All right, thank you.
All right. All right, I'm going to go ahead.